Here I'm showing an example of some layout for SRAM 6T cell. Again, the cell size is critical because we're arraying potentially hundreds of thousands of these cells in large SRAM arrays. So the smaller you make it, the better, as always. And so this particular cell is being shown as 26 by 45 lambda. Industry, it would, the state of the art is even smaller. So the other thing that you can do is, since you know you're arraying these out into very large arrays, instead of making each cell all by itself, you can tile, you know cells are going to be next to each other. So you can create the cells where it's even more compact layer by sharing VDD and ground and sharing bit line contacts, etc. And so typically you will generate these cells instead of individually. This example is showing how you can create an array of a 2x2 array of cells to make it even smaller in order to share various different contacts and connections. So this is just an example here. So don't take it that this is exactly what's used by everyone in industry. Everyone's going to have their own design depending on their process technology and proprietary layout rules, etc., and processing capabilities. So in very small dimensions in CMOS, in order to make things as small as possible, what we really want to do is we want to avoid bends and jogs in both our polysilicon and in diffusion. And also, if we can orient all our transistors in one direction as much as possible and keep all of our polysilicon as straight as possible, we can compact our areas a lot better than if we don't have this. So this creates lithography friendly, and effectively there's a concept or a type of designing that's called thin cell layout that can do this type of thing. And so it's something that creates low area, and it also reduces the length of our lines for both our metal lines, our poly lines, our diffusion lines, and reducing length reduces resistance and capacitance of both internal to the cell and of your bit lines. So this is something that's used by various different players in the industry in order to compact the size of their bit cells as much as possible. So I'm not going to go into great detail on exactly what this layout looks like. It will change from one process generation to another. Just keep in mind that there is something called thin cell technology for SRAM cells. So here I'm just showing 5 different generations of SRAM cells. In particular, this is from Intel micrographs, and you can see that in the 130 nanometer and 90 nanometer, it looks like they were using vertical poly, and then when they went to 65 nanometer, they went to horizontal poly and transitioned to what was called thin cell at that point. And you can see that the 65, 45, and 32 nanometer all use the horizontal poly and this what they call thin cell technology, and that they got very steady scaling of their feature sizes and their overall cell area, kind of on a nice, pretty straight line graph as the feature sizes went down. And you can see that both Intel and IBM, as far as the scaling of their feature size and their cell area, were very much in line with each other along that line. And so The different players, even though they might have slightly different designs to their process technology and maybe to their bit cell layout, still manage to get very similar results as each other. So now that we've talked about the basics of the bit cell and reading and writing from the bit cell and how it's constructed into an array and columns, we need to talk about driving our word lines. And in order to drive our word lines, we need decoders. So we'll have, for whatever our word size is, we need n number of bits to come in order to drive 2 to the n number of word lines. So down below we've shown just 4 word lines, word 0, 1, 2, 3. In order to drive 4 word lines, we need 2 to the 2 power, so we need 2 bits coming in. So A0 and A1 are bits coming in that then get decoded in order to drive the word lines. So the decoder consists of 2 to the n. I don't know why they have an n input, 2 input AND gates, and then we need 1 AND gate for each row of memory, and we can build those AND gates either from a NAND function or from a NOR gate function, depending on if we do a NOT OR function. So down below, shown 2 different ways of doing it. One with static CMOS, where we have A0 and A1. We're generating A0, A0 NOT, A1, A1 NOT, and then we tap off from the appropriate combination. There's 4 different permutations of tapping off from those that we can get to then decode word 0, 1, 2, and 3. The AND function is a NAND function followed by an inverter. We use that because since the word line is generally driving multiple bits, if we have like an 8-bit word or maybe a 16, 32-bit word, we're driving a fair amount of capacitance. It's done most efficiently with an inverter rather than like a NAND gate or a NOR gate. So if we have our NAND gate driving that inverter can be fairly large size and not load down the AND gate quite as much, or as nearly as much as the word line would load down the NAND gate. So having a 2-stage function there helps us then have the inverter driving the word line. In pseudo NMOS, we could design something where it's more like a NOR function coming in followed by 2 inverters, and having 3 stages there, you can get even more, a little bit of more gain when in each of the 3 stages, and so you could have maybe a slightly larger output inverter. But again, I'm not a fan of pseudo NMOS, so I probably wouldn't do that, but there could be a particular application where it might come in useful. So here we can see just an example again, just a stick diagram example of what the decoder layout might look like. Keep in mind the decoder must be pitch matched to our SRAM cell. And we said in modern designs the SRAM cells are skinny cells, so that requires the decoders that are pitch matched to them to also be skinny cells and be very skinny gates. So, so the decoder layout in general, as it's hooked up to an array, is not going to be our standard cell library. It's going to be a specialized library that's specifically for decoders going into these arrays. So that's the main reason why I'm presenting this slide. Keep in mind, you don't use regular standard cells when you're driving word lines and bit lines for arrays. You have to make sure to pitch match to your rows for your word line cells and pitch match to your columns for your bit line drivers and and read devices. Now in the previous slide where we were doing a decoder where n was 2, each word line was driven by a 2-input NAND gate. If we have, let's say, n is equal to 4, and we're decoding A0, A1, A2, A3, so we have 4-bit input to our decoder, then each word line would need a 4-input NAND gate. Now, when we start getting to 4-input NAND gates, or larger than 4-input NAND gates in particular, you can see the series NMOS devices are going to become very slow if we're using a single stage to do that driving. So typically what we wind up doing is, as we get into even n greater than 3, so n4 or more, we tend to start breaking that into smaller gates that are multiple stages of smaller gates. So below is shown for n equals 4 as an, or so for, n equals 4 in this case, we have 16 words, so it's 2 to the 4th power, so we have 16 words, and each of those 16 words needs either a 4-input NAND gate, or we can do as shown below, where we have two 2-input NAND gates followed by a 2-input NOR gate. And so in this particular case, we can get a little bit better drive strength and better delay through smaller gates, but a larger number of smaller gates. So here we're showing the concept of doing pre-decoding. If you go back to the previous slide, you would see that for each word line we had two 2-input NAND gates followed by a 2-input NOR gate. Turns out if you look at all 16 word lines, a lot of those 2-input NAND gates that you had for each word line are kind of replicated and redundant from, like, let's say word 0, going from word 0 to word 4, you might see that the one of the NAND gates was actually in common between, or had the same kind of input tap-offs and output value between word 0 and word 4, just as an example. So what we can wind up doing is, instead of having 2 NAND gates for each word, which gives us a total of 16 times 2 is 32 NAND gates, we can do some pre-decoding where we look at the lower 2 bits, for example A0 and A1, and create 4 combinations of A0 and A1 with 4 NAND gates, and then create all 4 combinations of A2 and A3 with another 4 NAND gates, and then we tap off from those pre-decoded values to go into the NOR gates for each of the 16 words. And in this case, we only need 8 NAND gates instead of 32 NAND gates, and we still need the 32 NOR gates to drive the final word values. But effectively, we can do this pre-decoder to save area. It's the same total amount of path effort, but it will save us area, and it will save us some amount of power as well in order to do this same logical function. So the word line drivers that we just covered are basically driving the values that go along the word line rows. Next we'll be covering the logic that we need for the column circuitry, and so there's certain circuitry that's required for each column, and the things that are required I'll go into in more detail in the coming slides are bit line conditioning, sense amplifiers, and column multiplexing, depending on the type of array that we're doing, You might not always need column multiplexing, but in some cases we'll go into when you do need it and don't. Bitline conditioning is something that we need for each column. We've already kind of covered part of this, and so the part that we've already covered is, as I mentioned previously, we need to pre-charge our bit lines to be a high value before we do our reads. And so we have two PMOS devices that are clocked by our clock, and when the clock is low, or the value going to the PMOS device, so if it's a 5 bar clock going in there, when the clock is high, 5 bar is low. But when the actual gates of the PMOS pre-charge devices are low, the bit line and bit bar will be pre-charged. In addition to that, typically we'll also have a equalize transistor PMOS device that's tied between the two bit lines, and that's because if when one bit line was pulled low during, let's say, a read or a write, when we go back to pre-charge, the bit line that was already high, since it's fully high, it might wind up being all the way at VDD, whereas the other one, during the time that we have to pre-charge the bit line or the bit bar value, we might only get up to, let's say, 98% or something of VDD. We might not get it fully there. And so, so we don't want any differential at all on the two bit lines. And one of the ways we can do that is when we first start pre-charging, in addition to trying to pre-charge the side that was low, we turn on a equalized device between the two bit lines, and it will help pull the bit line that was high, it will help pull that low a little bit to equalize to the other one, and then as they're both pre-charging, they'll be closer in value to each other and hopefully be almost exactly the same value by the time that you finish pre-charging and go into the next cycle. Now, the next thing that you typically need for each column is what it's called a sense amplifier. In effect, our bit lines, when you're looking at your bit lines, in most modern IC designs, they have many cells attached. You typically do not have a 4-entry or 8-entry array. So you'll have, for example, a 32 kilobit SRAM will have 128 rows and 256 columns, so 256 bits wide, and 128 word lines or entries into that. So that means there's 128 cells on each bit line. And when you go back to our propagation delay, keep in mind that that's proportional to the capacitance on whatever the line is. So in this particular case, even with shared diffusion contacts, so if you have 128 cells on each bit line, and even if you're sharing the diffusion between two different bit cells, that still means you have 64 capacitance units of diffusion capacitance because of the number of bits that are on each bit line. So 64C is a very large capacitance, which means you're going to be discharging as you're trying to write a bit line, or not write, as you're trying to read out of a bit cell, and reading out of a bit cell is going to discharge either the bit or bit bar side of the bit line. Keep in mind it's being discharged through really small transistors, because we're trying to make these transistors as small as possible to have our array size as small as possible. This means a very small current on a very large capacitance. It's going to be a really large delay if we need to get it discharged all the way from VDD to ground. So typically we don't have, several slides ago I showed just having an inverter to read out the value. In general, for most designs for SRAMs, we don't have an inverter there because that would mean we'd have to go past a 50% point in order to flip the inverter, but we don't have the time, or we don't want to take the time to get to a 50% point. What we wind up using is we use a sense amplifier to detect the difference between bit and bit bar, and we can figure out which one has been pulled down, even though it hasn't been pulled down far enough to cause an inverter to switch. If we're doing a differential sense amplifier between bit and bit bar, we can detect which side has been pulled down, and we can detect which side is supposed to be 0 and which side is supposed to be 1. Here is shown an example of a differential pair amplifier. This might look familiar to those of you who have been in EE 323 at Oregon Tech, where we effectively have on the bottom transistor N3 acts like kind of a current source, and then we have N1 and N2 are a differential input for in effect a voltage amplifier differential input, and P1 and P2 is in effect a current mirror load that we have on this differential amplifier. And so we have our inputs are bit and bit bar, and then our output can be where sense and sense bar are shown there. And so we just need a large enough, we can basically sense a fairly small difference between bit and bit bar, and that will cause sense and sense bar to either be pulled up to close to VDD or pulled down close to ground, and then we can send that into the outputs of sense and sense bar into normal inverters, for example, to get a fully rail-to-rail signal of sensing our output to be high or low. So this type of differential pair doesn't require any clock, but since the value, the N3 is always turned on there, it always dissipates some amount of static power, so it might not be a good choice for being a low power design, but it might be something that's a fairly fast design, so depending on your trade-offs between power and speed. In general, probably won't wind up using exactly this type of design because of the power hit for most designs. Rather than the differential pair amplifier that we had in the previous foil, most designs you'll see something probably more similar to this type of clocked sense amp. A clocked sense amp saves power. What you wind up doing is you start with the clock low and start evaluating or reading a given bit cell, and bit bar will start changing, or one of them will start falling. Whichever side is being pulled down will start getting pulled down. When your sense clock is low, bit and bit bar are effectively through the PMOS devices that are called isolation transistors in the schematic shown here. Those PMOS devices, when sense clock is low, will be on. So one side, as it's being pulled low, will go through those PMOS devices and be pulling the lower part of sense and sense B low, or one side of sense or sense B is going to be pulled low. The other side is going to stay high. Now, when sense clock goes high, the isolation transistors turn off, but we'll have a differential voltage on sense and sense B. One of them is going to be higher than the other. Then when the clock goes high, in effect, the pull down will be turned on, and the NMOS and PMOS back-to-back inverter that's shown there will detect which side is lower than the other and will help, in effect, pull that side lower quicker than the other side. And so whichever side is higher than the other will be pulled higher. The side that's lower will be pulled lower, and in effect, this will wind up resolving to a value of 1 and 0 based on whichever side was higher than the other will be the 1, and whichever side is lower than the other will be the 0. And this will resolve as long as you had enough differential before you had your sense clock go high. And the reason why you have the isolation transistors is that way it cuts off sense and sense bar from the really high capacitance bit and bit bar lines, and so it will switch a lot faster, and it will also use less power than the previous design because it doesn't have the static power consumption. Once it resolves, the power will go back down to 0. In effect, there will be just a small amount of leakage through the back-to-back inverters, but you won't have any constant current through this device once it resolves. And it will resolve pretty quickly because the amount of capacitance on sense and sense bar is pretty low once the isolation transistors get cut off. Now, one final note about the bit lines and sense amplifiers is keep in mind the sense amplifiers are trying to detect a fairly small differential between bit and bit bar. And since they're trying to detect such a small differential, they do a pretty good job amplifying small differentials, which namely noise is something that can create a small differential. So if you have, for example, your bit and bit bar your bit lines are going to be vertically driven, and bit 1 and bit 1 bar are going to be pretty close. Bit is close to bit bar for bit 0 is close to bit of bit 1. And so if you have, let's say, bit 1 is trying to pull down, but bit 0 bar is trying to stay high, bit 1 will couple onto bit 0 bar, and we don't want that. So one of the ways that we can try to prevent, or not really prevent, coupling noise, but we can try to minimize coupling noise, is to do twisted bit lines. So if you look at the down below, you can see where halfway along, let's say, the bit line, we take bit 0 and in effect take bit 0 on the left hand side and transition it to the right hand side, and bit 0 bar on the right hand side and transition it to the left hand side. And then for the odd bits, instead of doing it halfway along, we do it at 1/4 and 3/4 of the way along. Now you can see that bit 1 will couple a little bit onto bit 0 bar at the top and a little bit onto bit 0 at the bottom, but in the middle, bit 1 bar couples onto bit 0 bar for a little bit and bit 0 for a little bit. And so if you look at the way that bit 0 and bit 1 couple onto each other, they kind of mirror each other to a certain extent, and so you get the same amount of coupling onto bit 0 and bit 0 bar from bit 1 and bit 1 bar, and the same thing from bit 1 to bit 2, bit 2 to bit 3. So if you go look at this and make sure you understand this concept and see how there's the same amount of coupling of each neighboring bit on each other by the by the bit side and the bit bar side of each of the neighboring bits, they get the same amount of coupling from each side. And so in effect, any noise from coupling capacitance will be equal from either side for bit 0 and bit 0 bar due to bit 1 and bit 1 bar. They should see the same amount of coupling noise on both sides of the bit. So if you didn't totally understand that, pause here, look through it, or read in the book to get more information, but make sure you understand this concept.